And if you look at this second data set, and this is a data on oscillation measurement taken from 1955 until a few years later, and data is taken each month, every month. So it is an equally spaced data set. So because if the outcome of interest is only one, so this can be analyzed using univariate time series analysis. On the other hand, the multivariate time series analysis is also the same, except for the dependent observations, or the observations of interest measured, is more than, or are more than one, So for this example, you got time, and this value 1 is one of the outcome of interest. Value 2 is another outcome of interest, and value 3 is another outcome of interest. Okay, let's go and see time series as a single observation. A time series is actually a single observations on the stochastic process. Stochastic means it is random, and with that data we want to make inference about the properties of the underlying stochastic process from a single realizations, a single observation at each time. So to do this, you need to make assumption. The first is the assumptions of stationarity, and the second one, because of the stationarity, there is degree of dependence between two random variables in the stochastic process, and this dependence decreases as the time interval between them increases. All right, the further apart, then the dependence gets less and less. And then why time series? Because with time series data we can we can analyze data that are correlated, right? And each observation does not provide entirely independent information, dependent on data before it, right? So because of this dependency, you can't use standard regression formula, because it will introduce errors, which is very small errors, and because of that, the inferences for time series, if the dataset is analyzed using traditional regression, the inferences becomes invalid. So to handle the problem of time series, especially dependent observations, we use special analysis on the time series, and we hope to obtain valid inferences. We hope to obtain efficient estimates and inferences. That's basically our interest, right? When you have data, time series data, if you look at figure 1, you can see the number of bursts on the y-axis, and the week number on the x-axis. So you can see from week 0 to week 50, week 100, and week 150. So it is a 3-year data, and then you got this line graph Okay, so you can show that you can describe this time series analysis by providing this plot, and also by providing summary statistics. On top of that, you can smoothen the curve, and when you smoothen the curve, when you smoothen the data, not the curve, you smoothen the curve, you smoothen the data, you'll get a smooth curve. You can see the trends, all right? You can see the trends, and from this time series, you can decompose the time series into different components. If we look at one example for, in this case, association of daily mortality and air pollution. So this kind of data, if you got daily time series and you got data every day on the number of deaths and the level of air pollution, you got daily data and you take every day, then every week, every month, and a few years, you can see the annual trends. Over 1 year, this is called trends. And within a year, you can see the seasonality. And within that seasonality, you can see monthly variation, weekly variation, and daily variation. So you have trends, you have seasonality, and you have variation. Annual trends can be influenced by changing medical practice, population size, smoking rates, and other factors that vary slowly. There is also a component called seasonal component, and seasonal component reflects the effects of a faster varying factors, for example, infectious disease epidemics, weather, and you can have also daily variation, which indicates a very acute a change in the factor. Right? These four plots show the observed data, the number of births against the time. Then we can smoothen the data and obtain the smooth curve to see the trends over the 3-year period. And within each year, you can see seasonality. So you can predict trend, you can predict seasonality, and once you have taken care of those things, you plot the residuals, hoping that there is no more obvious pattern from your data. So here you can see that you have removed you have identified important factors in your data, and looking at your residuals, they are all right now. You can run time series regression model. Why? Because you want to explain the relationship between covariates or independent variables. So we got the dependent variable, which is the response process YT, the number of deaths, the number of suicide, the number of infection, and then you have predictors, and predictors are assumed to be fixed and non-random. And you might ask, why can't we analyze this kind of data using Poisson regression or using linear regression? Of course you can't, because the observations in the data are correlated, are dependent. So you must consider correlation into your estimation. So we can do auto-regressive models, AR, or we can use distributed lags model. We can use marginal models and also conditional models, but we won't go there yet for now, right? You must consider this before your analysis. Ask yourself, is there a trend, meaning that on average over that long period of time, does the measurement increase or decrease over time? And within shorter period of time, perhaps within a year, is there seasonality, right? Seasonality, seasons, quarters, month, day or week, and so on. Are there outliers? Is there a long run cycle or period unrelated to seasonality factors? Maybe certain conditions have a long cycle, right? Is there constant variance over time, or is the variance non-constant? Are there any abrupt changes to either the level of the series or the variance? Examples, okay. If you have this plot, if you look at the plot, there is no consistent trend. It's like, things are fairly flat. So there is no obvious trend upward nor downward. The series appears to slowly wander up and down around one line at 20.2. And this data is annual data for 99 years. So we don't have data for uh, month or week. So, we can't say anything about seasonality. There are no obvious outliers, but it's difficult to see whether the variance is constant or not. So this is earthquake data over the 99 years period. So if you want to do regression for this kind of data, if you got covariates or predictors, then you can use auto-regressive integrated moving average model. So we can use that model to predict the value at the present time using the value from the previous time. So the simplest ARIMA model for this one, where there is no trend, there is no seasonality, is to use auto-regressive lag 1 or auto-regressive order of 1. So the order of the model indicates how many previous time we used to predict the present time. In this case, we use one previous time to predict the present time. So we run auto-regressive 1 and we check the residual. Residual is the difference between the observed and the predicted values. We plot the residuals against the predicted values or fitted values, and it does not show any problems. They are scattered, random, and the variance looks equal. Let's say we have this plot over 70 years beer drinking. Here you can see there is an upward trend. Looks a little bit curvaceous, and you can see for each year there is seasonality, right? So you got trend, you got seasonality. There are no obvious outliers, and you can see there is increasing variations because the width of the observation at 70 is wider than the width of observation on the first observation. So if you have uh, an upward trend with regular seasonality, you can use classical regression method for trend and seasonal effect. Um, Plot the residuals and the fitted value, and you can see here classical regression has managed to remove um, has the classical regression has capture uh, the informations from your data, and residuals again fitted values, so scattered random equal variance plot. You might want to confirm the autocorrelation between observation by using ACF autocorrelation function, and you can see that the autocorrelation values range between 0.2 to minus 0.2 over different lag. So this does not suggest significant autocorrelation. So which means you don't have problems of autocorrelation. You can use classical regression. You might have heard about ARIMA, auto regressive integrated moving average, versus ARMA. ARMA does not have I, so does not have integrated. So let's see when to use what. Say you have sales data for drinks, and this kind of drink or data will be influenced by season and will always have some trend. So why there is trend? Because if when as the population increases, so there are more people, and more people are exposed to Western culture, so more people drink, so you can see the trend, upward trend. And you also note that within each year there are periods of where drinks are sold more than other periods, so within that year, so there is seasonality, and over the long run there is trend. So in this case you have trend and you have seasonality. Because of this, you may want to apply auto-regressive integrated moving average rather than just ARMA. Okay. So this is one example where you got a trend which is up and then stagnant, and you got also seasonality. So you have trend issues, you have seasonality issues. So you need to use ARIMA for this. And for ARIMA, again, ARIMA, you can have non-seasonal ARIMA and seasonal ARIMA. Non-seasonal, I think you can understand, is that there might be pattern, there might be trend or non-trend, but there is obviously non-seasonal. Seasonal ARIMA, there is trend or no trend, but obviously there is seasonal pattern of your data. How do we know whether there is important non-seasonal, or there is important seasonal seasonal data or seasonal pattern of your data, or there is none? You can use PACF, right? So the PACF here shows a single spike at the first leg, all right, and then there's no more, all right. And if you look at the ACF, you can see a pattern of decreasing values of ACF, right? So this suggests non-seasonal ARIMA model, but for seasonal ARIMA, you can see spikes at legs 1, 11, 12. So it means that there is seasonality there, right? Unlike this one, this is just decreasing. This one you got spike, spike, spike. This one no spike. It's just like there is spike there and then decreases. There is spike, decreases, and spike again. So there is seasonality there. Um, um, because this model has non-seasonal and seasonal MA terms, the PACF tapers non-seasonally following leg 1 and tapers seasonally that is near. Okay, we won't spend time on that. Okay, so that's basically the idea of time series analysis. It is an introductory level of lecture on time series. um, you can go you can read some of the references that you can read the references here. Okay, first is this time series note on Penn State Abilene College of Science on applied time series analysis. There is a nice website, introduction to time series analysis. If you want to try um, and analyze your data using R, then you can read a little book of R for time series. And there is a review paper by Zager, Irizarry, and Professor Peng from Johns Hopkins in the Annual Review of Public Health. Title is On Time Series Analysis of Public Health and Biomedical Data. With that, I thank you, and please read more to understand time series. Thank you.